So welcome everyone. We're now currently at the St. Denis field site with a number of people, and you should actually see on our YouTube stream a main slide introducing us to this place. So this is our live stream field trip to a location that defined basic principles of prairie hydrogeology in the 20th century. And as you can see today, researchers will continue to develop amazing things and discover amazing things at this field site. I'm Nicholas Kinner, and I'm going to introduce you to a number of people that are here at this site, here for the first ever live stream field trip that we have at the St. Denis site. So before we begin, I'd like to introduce everyone, but also to give a land acknowledgement. And as we gather here today, we acknowledge that we're on Treaty 6 territory and also the homeland of the Métis. We pay our respect to the First Nations and Métis ancestors of this place, and also reaffirm our relationship with one another. You'll generally see here, as I'm starting to move the camera across the scene, here's Chris Spence. So Chris Spence is a scientist with Environment and Climate Change Canada, and he's extensively worked here at this field site. Hello Chris, how you doing?
Hi, good Nick.
Yeah, if you could just say a couple of words about yourself and about what you've done here at this site.
Like I said, my name is Chris Spence. I'm a research scientist in hydrology with Environment and Climate Change Canada in Saskatoon, Saskatchewan. I've been working out at St. Denis for about 15 years now, looking at surface hydrology and surface and subsurface linkages. We maintain a sort of a network of piezometers, wells, flumes and weirs and climate stations that help us better understand the hydroclimatology and hydrology and hydrogeology of sort of a classic prairie pothole, undulating topography, agriculturally dominated environment. So I'm not sure where we wanted to start.
Let's go over to Andrew maybe. And so this is Andrew Ireson. He's with the Global Institute for Water Security. He's done a lot of work here at this site. Yeah, if you could say a couple words about yourself, Andrew, that would be great.
Okay. Hello everybody. Yeah, I'm Andrew, as Nick said, and I've been working here at St. Denis for about 8 or 9 years now. And my main research interest is subsurface hydrology, so soils and groundwater. And so today I'm going to show you some of the instruments that we put in at the site, looking at soil moisture and shallow groundwater and pond groundwater interactions particularly as well. Also lots of work on frozen soils that we might talk about as well. So as we walk over the site, we'll look at some different instruments that we've got going on.
And there's Seth. So Seth is a grad student that's with the Global Institute for Water Security. He's coming along to help us out on this virtual field trip. Yeah, Seth, do you want to say a couple of words about yourself?
Yeah, hi guys. So as Nick said, I'm an MES student, Master's in Environment and Sustainability student with Andrew, and we work a lot on frozen soils, and I'm here to help out with the field trip.
Yeah. So what do you think you're going to learn from this site, Seth?
Well, I've been at this site a couple of times, but I'll get the chance to look at some of the fancy stuff that you brought along, and also look at some of the things that Andrew is going to show. He's going to do some couple of very simple field experiments, and yeah, that will be interesting.
Great. And also over here, Morgan Bratton. So here, yeah, if you could say a couple words about yourself, Morgan.
Hi, I'm Morgan, as Nick had said. I just started my Master's of Environment and Sustainability.
Yeah, so as you can see, we're here at the St. Denis site, and if you look around us, you can kind of see it's typical Saskatchewan topography. And you can also take a look at the 3D camera feed as well too. We have a Met Station tower that's over here and a very, very interesting landscape. So we're going to start.
St. Denis, the St. Denis National Wildlife Area was created back in the late 60s as a partnership between the University of Saskatchewan and Environment Canada with the the Canadian Wildlife Service of Environment Canada, and it was first created to get a better understanding of how migratory birds do in an agricultural environment. And so in the 60s, it started mostly with things like bird counts, and just starting from that. And it's a square mile and a half landscape. Nick's been showing you that, what it kind of looks like. And what ended up happening is that as it kind of grew from sort of a biological and ecological study area into a sort of a more integrated one, because in the 80s and the 90s, the hydrologists showed up, and because they were interested in what sort of pond dynamics meant for the birds, so it became more important to understand what the water budgets were of individual ponds. And these were a lot of questions that were asked in the, like I said, in the 80s and 90s. There's a place not far from here, sort of across the road, that's part of the wildlife area, that's sort of nicknamed the Woo Slough, and that was one of the first water budget studies of a prairie pothole pond in this landscape. So we started to understand sort of, you know, how much precipitation fell, how much evaporation there was, groundwater flows into it. And then in the 90s, Masaki Hayashi started doing some work at Pond 109, which is we'll visit later, and that really that study really helped us learn some of the subsurface linkages and how groundwater behaves in different ponds, because and what's nice about Saint Denis is because we're sort of, you can tell here we're sort of in an upper location, but there's also some lower spots, so there's a diversity of different types of ponds that recharge the groundwater system or receive water from the groundwater system, sort of recharge and discharge ponds. So it's a nice diversity here that you can sort of sample in a very tight space. What followed from that is sort of like the linkages between the hydrology and the biology was sort of enhanced with, I guess, maybe 10 years or more ago, with sort of more hydrometeorology instrumentation. And there's the scaffolding tower behind Nick right now. We'll talk about that later, perhaps. And what's nice about Saint Denis is that right now you've got a nice, well, gosh, that's pushing 40 to 50 years of integrated ecology, hydrology, hydroclimatology, hydrogeology data that helps us understand the system and how everything works together. And in that sense, it's one of those few sites on the prairies, maybe some other ones being like Cottonwood down in the States in North Dakota, sorry, and Smith Creek perhaps, sort of east of here, that's been really nice. So it's, you know, it may not look like much, but it's actually got quite a rich data set here for this particular landscape. So that's kind of Saint Denis.
Hello. What would you like me to talk about now?
Well, let's maybe talk about the history, or a little bit about what you're doing perhaps at this site.
Yeah, well, I think we'll get into the detail of my work as we move over
as
here.
we start moving over.
So we could perhaps just say, can I say something about the watershed perhaps?
Yeah, sure.
So we're wildlife area here, and this is the bottom of a 10 square kilometre watershed, and so we have an upstream area. Actually, Chris will talk more about that, I think, in a bit with the hydrology of that. But within this 1.5 square miles, we have hundreds of wetlands, and as Chris was saying, they're very diverse in terms of their function, especially with respect to the way that they interact with groundwater. So from here, we're kind of standing on a plateau. It's almost, if you look at the topographic map, we're almost on a plateau, and to the north of us there's pond 1, and there's a complex of ponds that moves around sort of the outside, and down to the south, where we find the terminal pond for the entire watershed. And so up here on this slightly elevated land, we'll be looking at what's called Pond 109 in a minute, which is a classic recharge pond, permanent pond, and getting into that in a minute. So I think at this point it would be good to talk about the hydrometeorological instrumentation here, and why it's here and what we're measuring. So shall I hand to you for that,
Yeah,
Chris?
sure. I'll do that part. So one of the basic things that we need to know in this kind of a landscape is really just what the climatology is, and what we use for that are two climate stations. The first one, the one that's been here since the mid-80s, is actually across the road over that way. It's just a 10-meter mast tower, and it's if you can see, there's sort of a gold field on the other side of the road, and it's buried in there somewhere. It'll be hard to see, but that's where that's located. But maybe about 13 years or so ago, we had the opportunity to improve upon that instrumentation by building the scaffolding tower here, which includes radiation instrumentation, which we didn't have before. Actually, are you able to follow me with that?
Yeah, oh yeah.
Okay, so we'll get a good view of it if we come over here.
We can definitely go wherever you want to go.
And so keep coming this way. And so don't look at me, look at the tower. That's probably the better thing to do. So on the tower, that's again another 10-meter scaffolding tower, and what we were able to do with this is expand the instrumentation to include all the radiation components, so the incoming solar radiation and sort of long wave radiation, which is what you would maybe experience as a sort of like warmth, and then the outgoing, so whatever's coming down from the sky and then coming back up from the surface. And you can see the net radiometer is the thing that's pointing out from the tower there, and that measures those four components, and that with that you measure how much energy is coming into the system. And then what we were able to add with this tower that was really good is if you look at that white claw, the white instrumentation at the top that has the sort of the two claws facing one another, that's a sonic anemometer, and it's measuring winds in 3 different directions. And what we can do with that is if we measure that at a very high frequency, as well as the vapor content in the air or the air temperature, we can figure out what are called the turbulent fluxes. And the first one is called the latent heat flux, and that's basically the latent heat flux dictates the rate of evaporation or evapotranspiration from the land. And then with the temperature, we can figure out what's called the sensible heat flux, and that's something you sort of sense as warmth. So that energy that's coming down and we're measuring with the net radiometer is divided basically 3 major ways. It drives the evaporation and it warms the air, and that's the sensible heat flux, or it heats the ground. And what we're able to do with this climate station is measure those components, plus a number of meteorological things like just air temperature, relative humidity, wind speed, and wind direction. And we have a couple different levels. If you can see at the bottom, it's a bit of a breezy day, so the anemometer at the bottom is measuring the wind speed, and there's also something similar up at the top, so we can find those gradients and figure out evaporation or some of those turbulent fluxes in a number of different ways. So what this helps us do is figure out what the climate of the area is and the conditions on any given day. That drive sort of the pond water budgets, or how much is infiltrating into the ground, as well as some other things. One thing that we are missing from this site that we have over at the other one is a solid, or as a precipitation gauge. So that measures rain and or snow, whatever comes out, because all we have at the top of this one, you can sort of see it with the gold top, is just a rain gauge, so that just measures the rain, but we can measure the the snow with some confidence at the other climate tower. I don't know, did you want to show how a rain gauge works? So I'm not sure if anybody has any experience with this, but this is just a very straightforward and very common precipitation gauge, a rain gauge that many people use, and it's called a tipping bucket, and it's fairly simple in the sense that rain goes in, fills a little cup on the inside, provides some weight, and it tips, falls on Nick knows way more about this than I do, falls on something, completes a circuit, sends a signal down to a data logger, and you basically count every time it tips, and it's calibrated, and every tip can kind of mean like 1/10 of a millimeter of rain that falls. So if you want to look at the inside of it, that's the inside of a tipping bucket rain gauge. And so what happens is it comes in through the top, gets funneled in, lands in here, it does this. So if you're standing next to one of these things and it's raining, and you hear this kind of a sound, and just means it's working, right? So yeah, and that's a tipping bucket.
You could expand on snow, right? So these are no good for measuring snow.
These are garbage for measuring snow.
Yeah.
It's because the snow will fall in here, it'll cap on the edges, it'll crust, and well, clearly snow isn't getting down that hole, right? And so what you've got is other systems that they basically just capture the snow in a big bucket. And the most common these days, it weighs the snow in the bucket, and again, that's sort of calibrated to some sort of a voltage that a potentiometer perhaps would be attached to there to sort of produce that voltage, and then that's how you measure snow. Yeah. There's nuances and complications, of course, with measuring snow, but that's pretty much how it works. So, and the snow gauge, this is hung off the top of a tower. The snow gauge is actually mounted into the ground and leveled, and quite, they often have a concrete base so that they don't move and wobble, that kind of thing. So yeah, and that's collecting snow. The other thing we do, maybe I should mention on the subject of snow, is that every spring we have some snow courses that we run, and that just involves measuring along, maybe a couple of 100-meter transects across different vegetation types, the snow depth and the snow density, and we measure the snow density by basically taking a core, like a tube, shoving it into the snow, taking a core sample of that, right, and then weighing that. Because if you think of snow as more or less just containing two things, one is water, frozen water, and the other is air. The only thing that weighs something is the water. And if you weigh that, and you weigh the tube when it's full of snow and when it's empty of snow, and the difference has got to be the water in the snow. So that's how we figure out how much water is in the snow. We know how deep it is, and we figure out that density, and we just do that in a number of different places. We do it through some agricultural fields, some grassy fields. We do it over here at Pond 109, so we measure into the trees a little bit, and we get a nice diversity of different land cover types. And then from that we can sort of extrapolate out and say something like, wherever we measure in the trees is representative of the snow anywhere there are trees. And that's why a lot of people sort of measure the snowpack over such a large area. So, and that's how we do snow. And those records are nice because they go back, again, sort of another 20, 25 years. So, which is super nice, because what you can get to see is, once you've been out here for so long running these kinds of measurements and having that long observation period, is you get to see what things are like during droughts and during wet periods. So in this part of the world, around the turn of the century, it was super dry. right? And later on we'll talk about permanent ponds and ephemeral ponds and things like that. A lot of the permanent to semi-permanent ponds actually went away during that drought, and so it was nice to see that. And well, it wasn't nice to see that, but it's nice to be able to capture that, because then 5 years after that or so, we went into a sort of a record wet period where everything started to fill up, and it was interesting to see how the different ponds were able to fill. And we'll get to how that kind of works later on, I think. So that's probably, sorry, there's a, okay.
Okay, so we have one question.
Is it important or not reliable?
On the tipping bucket.
Yeah.
Okay, and who asked the question?
Justin
Okay, so Justin asked it.
All right, well, thanks, Justin. No, we don't often put a windshield around the tipping bucket. And that's a great question. I wish I knew a little more, or I could answer that better, but I've never really noticed too much of an issue with windshielding around when it comes to rain. Snow is a significant problem because it's not as dense and it blows around a lot more. But rain does have, there is an undercatch problem with rain, and I know there are algorithms that can be used to correct for that kind of thing. And I think that's usually how we adjust for it, is that we know what that particular tipping bucket will do in heavy, how it behaves in strong winds, and then we just apply those corrections afterwards. That's
because we measure the wind, right?
Because we measure the wind, right? And the best thing to do is what you'll often see next to, maybe not here, because we're measuring, what we'll do is get the wind at the top with the sonic anemometer and use that one. But in a lot of solid precipitation gauges, like the one we have at the other site, the anemometer will be almost right next to so the precipitation gauge will be here and the anemometer will be right beside it at the same height. This is an important thing, is you always want the anemometer at the same height as the orifice or the opening of the precipitation gauge. And that's important because there's a wind profile, right? The wind down here is a lot calmer than the wind up there. So that's why you want to measure it at that same height. So I hope that answers the question.
He says thank you.
Yeah. So
I can say a few words about evaporation and precipitation. So I'm just going to, and then we'll start moving on. So of course, in hydrology, precipitation is the most important measurement. It's the biggest flux that we deal with. And here at Saint Denis, we get somewhere between 300 and 500 millimeters of precipitation a year, with about a third of that in the form of snow. And the second biggest hydrological flux is evaporation. And so the evaporation fluxes from Saint Denis are about 300 to 500 millimeters. In other words, they're more or less the same, just a little bit less than precipitation. And this is an important characteristic of the prairies, because we have relatively low precipitation and relatively high potential evaporation. So evaporation is a complicated process and hard to measure. As Chris was showing you, that the eddy flux correlation device there is an attempt to directly measure evapotranspiration fluxes. But we can also attempt to calculate them using other meteorological variables such as radiation and wind speed. So evaporation depends upon a number of factors. Just quickly go through them. So first of all, you need energy to vaporize the water from liquid into vapor form, so to overcome that latent heat that Chris talked about. And then secondly, you need wind to move the moist air that's coming out of the ground and the plants away from the surface, so that you get this vapor humidity deficit, let's say, that allows the process of evaporation to carry on. So you're definitely going to need to measure the radiation, and you're going to need to measure the temperature and the wind speed and a number of other things. So I just wanted to show you this very crude, not that crude, but very simple and cheap weather station. It's a portable weather station, and it's a very nice instrument, and it's got a little anemometer here measuring the wind speed, and this gives me the barometric pressure, relative humidity, wind speed and direction. But what it doesn't give me is the net radiation, which is quite relatively difficult to measure, and one of the variables that we have relatively few measurements of around Canada. Of course, we do have it here on the tower, as Chris said, from that arm that protrudes out, where we measure the incoming and outgoing short and long wave radiation fluxes. So anyway, these meteorological variables, they tell you how much, let's say, the atmospheric conditions would like to take from the land surface in the form of evaporation. And this is the idea of potential evaporation or potential evapotranspiration that you might know about. And this number in the prairies in this area is probably around about 700 or more millimeters per year. So potential evaporation, that is what the atmosphere wants to take off the land, is significantly higher than precipitation, right? This is actually a semi-arid climate. So the more water, the atmosphere wants more water than we actually have. And because of that, one of the reasons that we actually have water on this landscape is because of the fact that we have these cold winters where the snow will accumulate over the winter and then very rapidly melt and inject water into the system more quickly than it can be evapotranspired back to the atmosphere. And so the snow melt is absolutely critical to the hydrology of the prairies. It's where our rivers get their water, the groundwater is recharged during snow melt, soils are recharged during snow melt, so that there's water available for evaporation throughout the growing season. So this is another very important characteristic of the prairies. There are a number of important hydrological characteristics, and the semi-arid nature of the prairies is one of them. So with that, we might move along, shall we?
Sure.
Yeah, maybe we can head over to 109.
So the ponds in this location have different names. Is there any type of history associated with the name, Chris? Or
There was a guy named Miller, Jack Miller. Is that right, Andrew? Yeah, right. Jack Miller, and what he did is he mapped all the wetlands across Saint Denis, and at the time, it seemed it was in vogue to instead of name things, to number things. They actually did the same thing at the experimental lakes area. So, in some sense, though, even though they're numbered, like it's almost become a name, right? Like Pond 109, that's the name of that particular pond is 109, or behind us Pond 1. We'll be looking over Pond 125 later on. Pond 50 is the Woo Slough that I was talking about. So the Woo Slough is kind of a nickname. And so he mapped all these wetlands. And I think maybe as we walk over there, Andrew, we can, as we walk, if this is okay with you, Nick, maybe as we walk we can sort of talk about the definition of a wetland and things like that, and what makes a wetland.
Sure.
As we go.
Sure.
Right.
So we're telling stories, we're talking about things, and we're also learning about the landscape. So what we're going to do, we're going to walk over to these ponds, and we're going to take the rest of our equipment a little bit.
Want me to take it?
Do you want to do the whole wetland thing that you just mentioned?
Huh? Yeah,
So
I guess so. I don't know, is that... Anyway, so, I don't know, can you capture that?
Yeah.
Okay, so as we walk past, we're going to walk over, as we walk over to the next hill, we're going to walk past a couple of different depressions, right? And this landscape, you okay, Nick?
Yeah, I'm good.
Okay. Should we just go?
Yeah,
Go. So The area that we're in is the prairie. Is one name for it is the prairie pothole region. And is it okay?
But yeah, I was just getting wonky for some reason. Sorry.
All right. Any.
Carry on.
So is the prairie pothole region, and one of the things that is characterizes this area is the undulating topography and the numerous depressions on the landscape, and these were created by as the glacier retreated, it left large pots of pieces of ice, and when these melted in place, they created depressions. Some people call it sort of knob-and-kettle landscape. So there's a lot of depressions on the landscape, and it's as Andrew was alluding to, it's a very semi-arid environment, and it's sort of relatively young, 10,000 years old, and it's got all these depressions all over the place. And what the result of sort of those three things is that there's often there's a complete lack of a mature drainage network, and so it's uncommon for streams to occur between the different ponds. And so they're often, in the United States, sometimes these are called geographically isolated wetlands. And they're just sort of like, there's one over there, there's one over there, another one over there, another one over there, right? And they don't have a surface water connection all the time. And so what's super important when you're sort of defining these areas, right? And what a lot of people do actually is sort of confuse the water that collects in the wetland, which is the pond, with the wetland itself. And often the wetland is larger than the pond, especially if you have sort of in the vegetation that's around it often. And if those soils have been exposed to sort of saturated conditions for sort of going in terms of like what defines a wetland, is they often use the soils to define sort of the extent of a wetland. So where I'm standing right now is not a wetland. Those wetlands hadn't been subjected to that kind of saturation before, but what's the word I'm looking for is with the soils. So is it?
There's a question.
Yeah.
Someone asked, what is the elevation range of the watershed?
Oh. If Andrew wants to turn around, and you can see the pond in the sort of foreground there.
Yes.
That's the bottom of the watershed. So if that gives people some sense of the relief, talking about, yeah, tens of meters.
That's what we call the terminal pond, the end. No water goes beyond that.
No, actually, so this watershed is not, and we'll get to this earlier, the watershed's not connected, is that pond, right? And we'll talk about this later about how different things work together, or how the different ponds, the water connects to and from. Are we okay, Nick?
Yeah, I think we're good for that. Sometimes, turn off if you don't change something. Okay, so let's.
Should we go into the?
Yeah.
Into the
Yeah. So if, well, we can keep walking,
Yeah.
right? But don't look at the, maybe show the pond?
Yeah,
Or
sure.
show the wetland?
Yeah.
But we can walk and show the wetland?
Yeah.
So we can keep... I'm not sure what you see, but you can sort of see the boundary here between some of the wetland vegetation and the wetland itself. There's a couple piezometers in the middle of it that have been installed to sort of measure the water table and the piezometric head underneath. And where that, if you show the, where the ground, the water in that pond, and maybe in a typical year, by July, in a wet year, maybe August, the pond is gone. But the wetland remains, right? Because it's, and the depth of that pond will vary from year to year with the precipitation and the amount of the snow that falls. Yeah, we can. So this is actually really important. I'll keep walking, if that's okay. What defines a wetland is actually a really important management decision, or management question, because a lot of agricultural policies are influenced by whether land is available to be sort of counted for insurance purposes, right? If it was a wetland, it was always a wetland. It was never something that you maybe could get credit for. So how that's defined is quite important when you're So I think I might, anyway, this is a nice spot because what you can see from here is a permanent to semi-permanent wetland, or a permanent to semi-permanent pond in a wetland, in pond 109 there, and then a number of ephemeral ponds sort of behind here. This is 108, so that's often dry. And then 5338, which is still part of that terminal pond, which we showed you earlier, and that's the very bottom of the watershed. And so you can sort of see a number of different types of ponds and wetlands, all from sort of standing here. But I think for now, for a little while, I'm going to pass this off to Andrew, because he's going to talk about pond water budgets and some other things. For a little while.
Okay. Thanks, Chris. All right, so we are standing here just next to pond 109, which is in the literature a very famous pond. Lots of people worked here. Masaki Hayashi, Garth van der Kamp did a lot of work in this pond. It's what we call, as Chris said, it's a permanent pond. In any normal year it won't dry out. During the drought in the early 2000s it did dry out, but I don't think it's dried out again since then. So it's what we call a permanent pond. The other important characteristic is, as I was saying at the beginning, we're on a kind of plateau here, relatively high part of the landscape. And so the water level in this pond is relatively high compared to all of the other surrounding water bodies, and also compared to the groundwater. I'll talk more about that later, but just the point is, this is since it's an elevated pond, the net movement of water from between the pond and the groundwater is downwards. And so it's what we call a recharge pond, in the sense that it recharges the groundwater system. Now, if we pivot around and I go over this side, we see This is pond 108A and this is pond 107. These are tiny ponds and they're ephemeral, so they're dry at the moment, just like the wetland we saw over there. So as Chris said, they're wetlands, but the pond within the wetland is dry. It's still a wetland though. So those dry out within weeks or perhaps a month or two of snow melt, as Chris was saying, in June or July. And however, just because they're not water doesn't mean there's no water in them doesn't mean they're not important. And in fact, they play a disproportionately important role in terms of groundwater recharge, which we've managed to show, well, we believe is the case, based on looking at water balances of ponds, so trying to account for where the water went as the levels dropped during the early summer, and also looking at isotopes, stable isotopes of hydrogen and oxygen, which can give you some information about how, by comparing different water bodies and the stable isotope compositions, you can speculate about how they are interacting or not interacting. So, the story I want, okay, shall I start with, okay, let's start with just the pond water budget. So what is the pond water budget? Think about it yourself. So the inputs of water come from direct precipitation on the pond. They also come from snowmelt and snowmelt runoff. So if you just imagine that pond there, it's going to be collecting runoff from a sort of, you could call it a basin or a catchment around the pond. And it will also catch blowing snow, and in fact that might even be the dominant input in many ponds. So those are your inputs, and then in terms of the outputs, you can have you could also have input to a pond from another pond, so spill from an upstream pond into a downstream pond. It's not happening in these ponds, but it does happen in other places, as we'll see. Now, in terms of the outputs from the pond, it can either go up to evapotranspiration or evaporation, or it can go in as infiltration into the ground underneath the pond. And so another thing we can do is we can look at how the isotopes become enriched throughout the summer, and that they become enriched because the lighter isotopes of oxygen and hydrogen evaporate more readily than the heavy isotopes. So you can see how the heavy isotopes accumulate, and from that you can sort of calculate the proportion of water loss to evaporation versus infiltration. And so what we see is that these ephemeral ponds have a disproportionately large amount of water loss to infiltration, which isn't really very surprising, given that they dry out so quickly. And so for that's one of the reasons that they're so important for groundwater recharge, and also easily overlooked, because you don't see water in them at the moment. And you see water in 109 there, and you think that must be a really important pond for recharge, and maybe it is, but there are many more small ephemeral ponds that are probably playing a disproportionately more important role. So that was the pond water balance. Now let's talk about soil moisture. Kind of jumping around a bit here, sorry about that. But we'll talk about soil moisture now. So if you look between these two ephemeral ponds, back in 2012, we instrumented a transect of, we put in a bunch of instruments along a transect to try and measure what's happening in the subsurface in great detail. So in particular, what we have is 8 piezometers that measure the water table, or they measure the hydraulic head, from which we infer the water table elevation. And we also have 3 nests of soil moisture instruments. And we'll go down and look at them in detail in a minute, but before we do, the basic idea here is to look at the way that the groundwater dynamics and the soil moisture dynamics are functioning on this transect, where you have essentially a pond and then a slightly elevated part of the land, an upland kind of, and then you have another pond. So we're interested in the lateral transfers of water in the subsurface between these ponds, and whether indeed there is an important subsurface pathway that's moving water under the ground from the more elevated ponds to the more lower ponds and ending up in pond 109. So you can see here hopefully what that transect looks like. So we're going to go down and look at our soil moisture instruments, but first of all I want to ask the students a question to think about something. So Seth here has what we call a capacitance probe for measuring the water content, volumetric water content. And what this probe does is, I'll just show the probe. You can see it's got these metal prongs, and it's going to measure the dielectric constant of whatever is surrounding these prongs. The dielectric constant is an electrical property. Well, I won't go into details about that, but it's an electrical property. What's important about it is that water has a very distinct dielectric constant compared to air and soil minerals and soil organic matter. So the dielectric constant of water is about 80, of air is about 1, and of soil solid materials about 5 or 6. So in other words, by measuring, so that bulk dielectric constant of a soil is dominated by the amount of water. So from a calibration relationship, we can estimate the volumetric water content using this instrument. So Seth is going to take a reading right here, and then he's going to take a reading down at the bottom. And what I want the students to think about is, what do you think is going to be the difference between the water content of the very near surface, so the top, say 5 centimetres of the soil, on top of this hill compared to down over there in that depression? So if you want, you can write your answers into WebEx. And Seth, you can go ahead and take the reading.
Yeah, so I'm going to stick this one right here. Stick it into the ground, and then press this one read button. And
don't tell them.
Okay.
We'll remember it, right?
Yeah.
Okay. So we've measured it here.
Okay.
So let's go down now. Oh, should we bring the?
Yeah,
or we could leave. Would it be okay to leave it there?
We can leave it.
I think it's probably fine because it.
Yeah, I think it's good to leave it there.
Yeah.
Yeah.
They get the 360 view then. Yeah. If you look at the vegetation around here, this is a managed site obviously, and some years really just kind of wild. So the vegetation within this transect's a little bit different to the rest of the site. But the good thing is we do have records of land use over at different parts of the site over the last few years. So it's a managed site where we have both cropping and also semi-native, semi-natural, you could say, vegetation. All right, so Seth is now going to take a measure.
Yeah, Justin said higher water content in lower area, all other things.
Okay, that sounds like a very sensible comment to me. Good. All right, so let's find out, Seth.
Yeah, so the moisture content there was up there was 26.2%. And down here is 34.1%.
Okay. So no surprises. It's wetter down in the lower areas, which Justin, absolutely right. Well done. Good. All right. So what we have here is one of these profiles of soil moisture instruments, and these instruments are being logged every hour, and I'll quickly go through all of them so you can see what we're doing. Now the main one, and we mount the probe on a PVC tube. We auger a hole in the ground, we ram it in to the ground, get a good tight fit, and then we wire it up to a data logger. And so we've got 7 of these at depths ranging from the very surface down to 3 meters below the ground. And they are, you can see the sticking up pipes here, they're just, this is them, right? So this instrument, as well as measuring moisture content, also measures the temperature and the electrical conductivity. And the fact that it measures temperature is extremely useful here in the prairies. And the reason it's useful is because we get these frozen soils. And so from just this single instrument, we know the depth of freezing based on the profile that we have and the temperature and how frozen they are. And that gives us a lot of important information about the winter processes, and in particular what's going to happen in the soils during the melt period. So this is an important story, right? So as I've already told you, the snow melt process here is a dominant in terms of the hydrology. So the very rapid melt event is where most of the water comes from that's used in rivers and groundwater and soil. So the soils determine what happens to the snowpack when it melts and the rain that happens during that period. So if the soils are very dry and they're frozen, the snowpack can melt and infiltrate into the soils, which is generally desirable because that's what you want. You want nice wet soils. On the other hand, if you have saturated soils that are frozen and you get this very impermeable conditions during the melt period, what happens is you get more runoff. So more of that snowpack is partitioned into overland flow, and that overland flow can fill up ponds, can cause ponds to fill and spill, and can generate floods and can fill up rivers. And so flooding, we had major snowmelt floods. We've had major snowmelt floods in the prairies over the years, periodically, right? And this is a very damaging phenomenon, to farms and to roads. Roads get washed out or submerged, and it's all to do with not only how much snow you have at the time of melt, but also the conditions of the soil. Okay, so it's really important. The infiltration capacity of the soil is very strong. Using these instruments to construct what he calls soil freezing characteristic curves, which is a bit like a soil moisture centigrade. So that's the frozen soil story. Now the other thing we measure here, which is a more generic thing, is with this instrument. This is a tensiometer, and it measures the matrix potential in the soil. So the matrix potential is a measure of how tightly the soil is holding onto the water. And the way you take a measurement is you fill this tube with water at atmospheric pressure. This is a ceramic tip, so it's porous ceramic tip at the bottom. So water can move in and out through that, but nowhere else, everywhere else is sealed. And you bury it in the soil, so it becomes in connection with the soil, and the soil will draw water out of the tensiometer by forces of capillary attraction in the soil, right? So the water in the soil is bitter, and then we just measure the pressure in the water column that's left, and that gives us this measurement of the matrix potential. So the drier a soil is, the higher the matrix potential, the harder it will suck water to try and bring it into its pores. So if we simultaneously measure matrix potential and water content, we can construct what we call soil moisture characteristic curves. That's the relationship between volumetric water content and matrix potential, and it's an important characteristic for how the hydraulic properties of a soil. And then the other thing we can do with this is we can convert from matrix potential into hydraulic head. And of course, hydraulic head, we're going to talk more about in a minute, is it drives the moving because of the gradients. This is all below the ground here and measuring every hour into our data logger. Nicholas? And Seth, I'm going to box here. Okay, all good? All right, itself going. This has been going for 7 or 8 years. Up all of our probes I just talked about. At some point, as you go down below the soil here, you will hit a water table. We use a piezometer. A piezometer is it's very simple. It's a PVC tube which is perforated at the bottom, allowing water to move in and out.
across what we call the screen. So this one, for example, is 4 meters deep below the ground. So it's a 4 meter PVC tube, and at the bottom it's open through this screen, so water can flow in and out between the ground and the tube. So water will rise up in the tube based on the hydraulic head until it gets to some static level, and we then just measure that static level by, as Seth is about to demonstrate, using what's called a well tape or a dipper. Deep when it hits water, okay, and the rest of this is just a measuring tape. The beep. 51. Take that off. So, but just to very quickly, the pressure increases with the weight of water above you, and so and a gravitational head, and so you simply sum the pressure. From this piezometer, we can infer that there's the hydraulic head in this piezometer is about something like 3.59 meters below the ground surface. And Seth is now going to tell us what it is in the second one. This one is, I'm going to get this right. This is 6 meters. This is 6 meters below the ground. This is installed. Okay, so the tube goes down 6 meters, and then the water level is 3.59 meters below the ground.
This is
the same, 3.59 meters below ground, roughly. Okay. If you do it properly, you'll find that both of them have the same exact hydraulic head. But this one is measuring a depth between these two piezometers. In other words, there's no vertical gradient in the saturated zone at this site, or no significant vertical gradient. It's maybe a very small downward gradient, but you have to measure it very precisely to get that. So that tells us that there's basically not much happening with the groundwater flow, at least in the vertical direction. Check out the gradient, and what I would find when I do that, because I've done it many times, is that at this time of year there is no hydraulic gradient. The water table is just flat and is about 3.5 meters below the ground. So not very exciting right now. But when you look at these, okay, so quickly, as well as dipping those piezometers manually, we also install these instruments in them. So we simply tie this thing on a string or a wire so it doesn't extend, and submerge it in the water in the piezometer, and it's a pressure transducer. And every hour it just measures the pressure. And by measuring the pressure, we can work out that same water level. So we actually have hourly water table elevations at each of these 8 piezometers, and for about 7 years now or so, something like that. So we know what's going on in the winters and in the springs and the summer and everything. And so what happens is, if you just remember what the transect we're on, right? So we've got 2 ponds over there and there. So in the melt period, what happens is that the water table underneath the ponds jumps up. Not before snowmelt, but during and after snowmelt, it jumps up. And then what happens is the water table below me now, some days or weeks later, follows it up as the water eventually moves laterally below the ponds into this sort of upland area, and also some of the snow will infiltrate down from above. So you get this kind of water moving up below the ponds and then to evapotranspiration, and also some lateral movement, probably over towards pond repeatable. What we also see is that when you get very heavy rain, it came right up to the ground surface immediately following a rainfall event, and then it dropped down again pretty quickly after that. So these dynamics of groundwater are very interesting here, and what's kind of important about them is that they also flush salty. It's rich in sulfate salts, and those sulfate salts get cycled of the ponds, and also nutrient input and output through the subsurface. And that's it for now here. I'm going to take a break, and we're probably going to have a hike, unless there are any So carry on. And why don't you start walking? Oh, shoot. What are we doing here?
I think we're going good. So this green at the very bottom. You wanna walk with it?
Okay. I think a badger lives there.
Yep.
So I think the plan was for us to walk this way
Yep.
to the end of that ridge so we could see
Yeah.
the wetland complex, and then 97's over there. Is that fair?
Yeah, I think
Yeah.
that's good.
Okay.
Yeah. So
Sure.
and then pond 97 is.
Oh, and what do I do if it does that?
Oh, sorry.
No, just press and hold. Okay.
I'm just going to check it.
Oh.
I want to check.
Okay. Yeah. So you can see those 4 yellow stakes.
Yeah.
So there's one there, and then so one will start there, and then it goes out to there, and that's one whole transect, and it goes through the pond and through there, and then the other one starts here, and then I just saw it. Oh, it's behind the tree. Yeah, straight out that way.
Oh, okay.
Yeah. And that's the other, so that's the big X that, so we go through the pond. That's better. Hmm? LiDAR?
out here.
Yep.
and-
Yep. Yeah, we couldn't.
It's nothing to do with
Um,
cellular, like where we're shifting.
We couldn't do some of the hydrological analyses
Why that?
without it,
Mhm.
because as I'm not sure who asked
We're
the
good.
question about the relief, but
Okay, so we're going to move on, everyone. We're just heading over to the ridge.
But it was,
So we're heading in that one direction.
You okay?
Yeah, it's good, but I think that's good enough.
So one thing that's interesting about if you look at Pond 109, I mean, these guys can still keep walking, right? We can pause for a second.
Yeah.
So if you look at all the dead trees in there right now, so after the drought of like 2000 to 2004, it got super wet in this part of the world, and the pond level in this wetland rose quite high and was sustained for years. And one thing that characterizes a lot of the wetlands around here is this willow ring, or these trees around, right? And you see this, you know, in the wetland behind us and all those wetlands over there, right? But what happened is that that area that willow ring was inundated for so long that that it killed a lot of the trees, right? And so it's just, you know, recently where we're sort of getting into more normal conditions where the water level's lower, but all those trees are dead and decaying now, right? And it's interesting, there's a few people at U of S that do carbon flux work on these wetlands, and it's super interesting the cycles that these things go through. And for most of the time they're a big carbon sink, right? Because it's promoting the growth of these trees. But after a drought, when it gets super wet, there is actually a big burp as things get flooded again. But anyway, we can keep walking. It's just one thing that I sort of noticed.
And pond 97 is in this direction. It's in that direction. Okay.
Are we doing all right for time?
Yeah, I think so. We're 2:25, so.
So do you want to carry on with the plan as discussed up to the?
Yeah, as long as we sort of see you.
Yeah.
Yep. Okay. All right. I'll so for a long time, I don't know if people can hear me or not.
Oh yeah. They
Yeah. Okay. We can walk and talk.
Sure.
Right.
Yeah.
So for a long time, the conceptual model of how water was exchanged between all these different ponds was such that there was basically sort of recharge pond, right? It's up high. It's got a sort of a positive water budget. Water comes in. Some of it's allowed to seep out. And move down slope, and some of that water will go through a through flow pond like this one over here, and then it'll eventually go down to the ones that sit at the lowest spots on the landscape, and those are the discharge ponds, like that terminal pond that we pointed out earlier, that's at the bottom of the watershed. So, and that's how the exchange of water and the water budget of each one of these diagrams that some of you might have seen that show these sort of big, deep flow paths. What was interesting was about 20 years ago, as we were coming out of the drought, the water levels in many of the ponds here and across the prairies and in North Dakota, right, started to fill and fill and fill. Like it started in about 2007, and it continued on for the better part of 10 years, and it got very wet. And so what people started to notice happening is that ponds were filling and exceeding their capacity, right? So if you look at this pond here, you can sort of on the left side of it, that's sort of the low end of the pond, or the low end of the wetland, right? And so what would happen is there used to be a pond in here, and it filled up and filled up and filled with water until it couldn't hold any more water. And then the water kind of spilled out the side. And then we get this, and this blew people's minds. There was a surface stream, an ephemeral stream that came out of that pond and went down into the next pond. And the idea that there would be surface water connections among these ponds was unheard of for a lot of people. We'll keep walking, right? And around the same time in hydrology, there was new theories about thresholds being batted about for all sorts of things, and one of them was this sort of idea of filling and spilling, and so what people took, they took that concept and said, oh my gosh, this is what's happening everywhere across the prairies. Is the think about wetlands as less individuals or
connected system.
Yeah, as a system that can connect and as a complex
and
right?
disconnect as well too.
Right, and so and this became very important because during this wet period, there were a lot of floods in this part of the world, right? And so there were places that were providing water downstream that never had before, and so what you ended up getting is a system where this wouldn't have necessarily contributed, this area, this little swale in here, none of the precipitation that falls in that area would have ever seen a major river for a long time. Now, this place, it doesn't connect up, but in other places where it may have, it actually did, right? And so if you just think of like flow as sort of a volume that's going by, and volume is really just the depth times an area. There was like huge areas that were opening up to floods, which just meant there's going to be more volume moving downstream, right? And in some ways it's as simple as that, right? Is that as you increase that area, you're going to increase the floods, right? And so people started to see these things as a complex. And so let's walk a little bit further. And so what we're coming up to now is part of that complex. So this is pond 125 or 126 perhaps. And we saw pond 1 earlier, which is over to our left behind that hill now. But for a while, there was an ephemeral stream that came down into pond 1 and flowed through these ponds, sort of down through this valley, and then out and around, and then it ended up in that terminal pond. And so for a long time, there was this paradigm shift at the time where it's like, oh my gosh, right, maybe a lot of the fluxes, right? Rain came out of the sky, snow blew into the depression, it melted, filled up the pond, infiltrated in, and it sort of moved sequentially sort of through the recharge and the through flow and the discharge ponds. And what was great about St. Denis at the time is because it had this super long record of pond levels. You could look back through time, through the drought and even before that, and you could sort of see where like pond number 1 behaved in a certain way. And it would kind of go up and down like this. And then it would shoot up. And its water level would go high enough to sort of spill. And then all of a sudden pond 125 would go up. And this would all be in the record. And it was actually like staring us in the face the whole time, right? And from 125, then 97 would go up, and then pond 90, right? But what we noticed is that during these sort of long cycles of precipitation, sort of dry, wet, right? The pond water levels would do the same, but they would all kind of be lagged, right? And what it was is that a lot of these pond water levels, there's the groundwater that's kind of going on in the background. But when they get super high, that's because there's the hydrological connections are opening up. The headwater depressions are filling up and spilling and providing water downslope. And that sort of goes sequentially through. So what you end up is that like pond 1's time series kind of looks like this. It kind of goes up and down every year, and then it'll do this, and then it'll drop slowly over time, right? And then it sort of does, and then it does it again, right? So you kind of go through this wet period where it goes up, and then it's slow drying over time. And you can sort of see that in all the different ponds around here based on their locations on the landscape and how big they are and what's upstream of them. And that's that complex that you kind of see. And it's an interesting phenomenon because then scientifically the pendulum swung, and it was this view that everything was groundwater dominated, and then that was tossed out the window, and then it was all surface dominated, right? It's like, oh, it's all fill and spill, and everybody was super happy, and they were batting around like that willy-nilly. And then Andrew and I got a student named Rosa Brannon, because one thing that we noticed as we came out here is that the pond water levels, and as the sort of the ephemeral streams were petering out of these things, if you looked at the evaporation rates we were measuring from the tower, the pond water levels should have been dropping way faster than they were, if it was all kind of surface dictated, right? But they just seemed to last forever, right? The stream here lasted until like late August, which is kind of nuts, right? And I remember Hock Woo, who the slough is named after, he was my PhD supervisor, and I remember telling him, oh no, there's a creek out there now, and he said, no, there's no creek out there, that's impossible. And I said, well, I don't know, it's a cubic meter per second that goes by in the spring. And but it should have sort of moved its way through and then slowly dried out. But what Rosa did was, if you look this way, you can sort of see a series of piezometers. These are just the white tubes on the hill slopes. And what she measured was the water table sort of through this valley and pond 125. And what she found was, like, I thought was absolutely fascinating, because what had happened is that during that wet period, not only are the ponds high, but the water table's super high. And in this place, like many other places, there's an exponential relationship between depth and hydraulic conductivity. So the shallow depths conduct way more water than the deeper ones. And so if the water table can rise up into that effective transmission zone, which is sort of a term that Garth and Misaki introduced, then you can actually move quite a bit of groundwater through shallow depths between the ponds and down the hill slopes. And what she noticed was that on the other side, where there isn't a pond, the water table tended to be below the effective transmission zone. But here, sort of through these piezometers here, and then the ones further down, is that wetland behind Nick was able to there was enough groundwater seepage out of that it was able to maintain the water table high enough into that effective transmission zone down into the other pond. So there was still a decent amount of groundwater that fed the pond, that maintained the water level, that allowed the surface stream to keep going so late. And what's super important about that is two things, is that whether there is a hydrologic connection depends on the distribution of the wetlands around the landscape. And the second thing is that if you have the right distribution of ponds and wetlands around the landscape, you can maintain those hydraulic conductivity connections so that if it continues to rain, more area is engaged in producing runoff and stream flow downstream. So what that means is that those landscapes that maybe have more ponds than others will be able to maintain flow longer than others will, than those without. And so this is an important thing because it comes down to sort of how you want to manage the landscape and the resilience of sort of water resources and water supplies. So having these ponds on the landscape, what they do is they hold water back at certain times when they're dry and lag and attenuate floods. But during a drying phase, because they have that characteristic of being able to supply water at certain times, you'll have sort of you'll have more water going into that dry phase. So they help buffer and maybe make things more resilient during sort of these wild swings that we seem to be getting in terms of wet and dry periods. So they're important to keep on the landscape. And so in terms of like a management of the whole place, the whole region, there's a big debate these days about how many wetlands do we got to keep, which ones are important, in terms of the balancing farm productivity and profitability with the security of water, and that also goes to the water quality of it all, right? The water quality. So this is a place like Saint Denis is super important because this is where we get the knowledge that helps inform some of those, at least that should help inform some of those policies, right? Anyway, I hope that kind of makes sense.
Yeah, that makes a lot of sense.
Okay.
Thanks, Chris.
Anyway, this is a wetland complex, right? So, did you want to?
Next step is on and forward.
We're running a bit short of time, but very, very quickly, I just wanted to quickly show you this. If you can see this red thing sticking out of the ground, it's another pedometer.
Is that too much?
This is a slightly unique pedometer in that it's installed in a confined aquifer. So the screen is located in a confined aquifer. So at the geology at this site is glacial till, and it goes down about 25-30 meters of glacial till, and then we hit a sandy sand lens or layer of sand, which is about 2 or 3 meters thick, and then we back into the glacial till again. Very typical of the prairies, right? So it's you get these sequences of clay-rich till and then sand. And so in the sand we have a confined aquifer, and indeed these are very often used by farms and rural residences as water supplies. And so this is measuring the water level, or the hydraulic head I should say, in the confined aquifer 25 or 30 meters below the ground. And what we see is that the water level in this piezometer is almost the same as in that pond at 125 over there that we were just talking about. But again, it's the pond 109, the recharge pond, has a higher head, the water's elevated above that level, but the terminal pond that we saw at the very far south is below it. So in other words, if you look at the hydraulic gradients, you have a potential flow path from the confined aquifer to the terminal pond. Now it's unlikely that there's any rapid movement of water because the permeabilities are very low, but it just tells you that the discharge pond, there's going to be no net movement of water into the ground, and if anything, there's going to be water coming out of the ground and into the pond. And as a result of that, that pond is very salty. The recharge pond is very fresh because it's just losing water to the ground rather than vice versa. So these instrumenting the confined aquifer here gave us some insights into these long-term kind of slow exchanges between the overall ponds and the groundwater system. Yeah, that's it basically. Little message there about the deep system. So, shall we move on? Or did you want to talk about snow?
Maybe we can talk about snow on the way.
Yeah.
What do we want to talk about snow?
Well, we've got to talk about blowing snow and...
Yeah.
Or have we already done that? Let's walk and think.
Walk and think. Yep.
Oh yeah.
Yeah, if you will, just grab this, and then you can just take it as we walk. If he wants to talk, you can just go and come back to the room. I'm just going to check.
Or is there a more direct route?
Oh, really? We can come back to maybe bring it.
Yeah.
And then, yeah.
Everyone doing all right with lifting? You know that Lauren's still there?
Yeah, she should be 97, so she should be around there.
Well, we'll find out.
We'll find out.
So our stream is healthy, but
That might be the problem.
Should we send Seth and Chris on ahead?
yeah. Do you wanna take
Yeah.
the camera or?
No, no.
Okay.
Okay.
So there's a bison ranch next door, and one winter it got so snowy, the snow drifted over the fence. They kept the bison there, and because of the way this is maintained, there's like so much grass over here, and so most of the bison left and came here, and I think they loved it because they would hang out here, they'd hang out in there, and some in that pond, some back there, right? And it was a bit weird, right? Because you'd come out here to do spring melt stuff, and you know, we would walk along the path that's over on that side, and there'd be this bison herd moving around over here, right? And you don't want to get too close to these things, but it was interesting. And like when the snow went away, you could just tell where they had decided to just sort of hang out, because the grass would just be gone.
Yeah.
Right? So this is kind of what I was getting at earlier, in that you've got this pond here, and then this intermediate one in the middle, and that's one of Rose's piezometers, and then 97 at the bottom, right? And so it's clear that this particular pond isn't getting as much water anymore, right? And it needed some inputs from that one, and this one's sort of slowly drying out. It's sort of in that recession phase, right? And then, but so it'll fill up super fast when this one starts to spill, and it goes. And another good thing, it doesn't necessarily, what happens is, as well sometimes, so some people talk about the fill and spill of prairie pothole depressions, but there's a guy down in the States named Scott Leibovitz, and he argues that it's not always fill and spill, because sometimes what'll happen is a pond like this that's kind of downstream is if they fill up enough, this will actually back up and it'll become one big pond.
Yeah.
And he calls that sort of fill and merge,
Yeah,
right?
okay.
Which is kind of what's happened, you know, at the terminal ponds down here, where you got a bunch of ponds that have just kind of coalesced together, right? And it's one big super pond now, right? So it's not just a sequential thing, because the landscape is so undulating, right? It just sort of like continues to fill until maybe there's a new outlet, right?
Yeah.
So, did that stop?
No,
I think he just held this one
Yeah.
until it popped back up.
Yeah, cool. For the winter.
Everything okay?
I think so. No questions.
Yeah, I'm back.
They may have come and gone. Yeah. Yeah, I think so. Maybe I can talk about snow for a little bit. So, like I was talking about earlier, that snow has a persistence to it. So once it falls, it can blow across the landscape and sort of fill depressions, get scoured from uplands. And so what ends up happening is that you end up with quite a diversity of where the snow ends up. You'll get maybe not that much in a place like this. Because it'll all collect in a depression like the one over there, or sort of behind you, Seth. The snowpack in those trees gets quite deep, and so what happens is the snow falls and it collects, and what it'll end up doing is that because it just blows so much around here, the wind blows, is that and Morgan was asking me earlier, how deep does the snow get? And I said, well, it gets as deep as the vegetation does. And then because after that, it gets this, and if it's not hard packed, it'll just blow away and end up in sort of a gully or in a pond and that kind of thing. So what you end up getting is, say at Saint Denis, sorry, at Pond 109, you'll get very low snowpacks up high, and then they'll build as you get closer to the pond. They'll get quite deep in the willow ring and the trees, and then quite shallow again just on the pond, because even off the pond, the snow will blow into the willow rings. So this is an important dynamic in terms of where the water melts and what it's available to, right? So it's a bit of a feedback system in the sense you've got a depression that was caused by sort of the undulating surface geology, superficial geology, right? So that'll end up there. It'll collect some snow, which kind of makes it wet, which helps plants grow, like trees, and then the trees grow and the vegetation grows. That traps more snow and it ends up with more water. Sure. And then you end up, yeah, that would be great. And then you end up with sort of shrubs and trees, and it's sort of this feedback loop that promotes the water. It sort of makes this drier versus that wetter, right? So there's all these factors that go into creating that. So I'm not sure which more. That's sort of the bulk of it. I'm sure John Pomeroy would have lots more to say about snow, but I think that's some basic take-home messages, right? So what's the plan next, Nick?
Yeah, we're going to go head over to another site. Okay. So Lauren Helmley, or Lauren Dick and Richard Helmley are doing a little bit of work over there, and so we're going to take a look at their field site. So Pond 97 or Pond 88?
Well, I saw them at 88 earlier.
Yeah.
And they said they're going to come here last, and they're not here, so they may have come and gone.
So this is 97?
Yeah.
Yeah, because I said around 3 or so.
What time is it now?
So it's around 3.
Okay. Hard to say.
Yep. So they should have been here, right?
Yep. I think they can access from the road there and then drive down.
Yeah.
Or maybe in here. They come in this entrance now.
So we'll see where they are, and we'll try to catch up with them. And as you can see, if you look very, very carefully, there is an ebullition sensor that's situated on this pond. And these are floating platforms. There's an electronic circuit that's out on that platform. And essentially what it's measuring is the volume of gas associated with ebullition. So ebullition is carbon dioxide, methane, and other greenhouse gases that bubbles up from sediments at the very bottom of this pond. And there is not really a good quantification of how much ebullition we actually have here in the Canadian prairies. And so the idea is to use electronic circuits, and these electronic circuits measure ebullition. And I was involved with the design. I actually did the design of the electronic circuit boards. Richard did the conceptualization of the floating platform, and it was a joint type of project between the Smart Water Systems Lab and other lab groups here at the University of Saskatchewan. So I designed the electronic circuit boards, and the idea is that the sensors are to measure ebullition, and they're to be networked, so that there's a network of different sensors in different ponds. And so this one is being tested at this time. So just coming back toward Chris, and so any news of Lauren, or?
I think she's probably gone.
Okay, they're probably gone. I told them to wait, but that's fine. I guess they've moved on, or?
Guess so. Unless we.
Okay.
Yeah.
So I think we've covered lots.
Yeah, I think we've covered a lot. Are we going to head back to the tower, or I guess, are there any questions that anyone has about this trip? And if there is indeed any questions, please let us know.
Right.
So, any questions? Okay, so would you want to say perhaps some concluding remarks, Chris, or would you want to say some concluding statements perhaps about our trip here?
No, not much. Thanks for having us.
Yeah,
Yeah,
and thank you. I think it was a great trip. I hope that everyone listening who's tuned into YouTube has indeed heard what we said. And yeah, it was great to have everyone here who attended the live stream. And thanks for sticking with us. Thanks for being able to be here on this particular trip. So Chris, thank you so much. Thank you very much for doing this. And Andrew, thank you again for actually coming out here and talking to us today. Yeah. So if there's no evidence of Lauren or no evidence of Richard,
I think we probably call it in. But just Nicholas, thank you so much for organising it. It was very well done.
Yeah. Thank you.
I think it's worked. Let's find out.
Yeah. And so another thing I'd like to just say, thank you so much to Seth and Morgan. It's been a great having you here, and thanks a lot for helping everyone out. Yeah, and it's the type of thing where it's students like you that really tend to drive this world a little bit better and make this world a little bit better.
Yeah.
So thank you so much for coming out. Thank you so much for doing research here at Saint Denis. And yeah, with that being said, I guess that we'll stop the live stream. So if there are no questions from anyone here, I'm just going to take one last look around the site. So as you can see, here's a pond with an ebullition sensor. And it's too bad we didn't have you here, Richard. It's too bad we didn't really have you here, Lauren. But the sensors are out, and as you can see, they're on the pond. And just looking around for a final last time, we're doing this live, and we tried to do this live from Saint Denis, which is a national wildlife area here in Canada, and also a site that has a lot of hydrological importance here in the Canadian prairies. So that being said, we're just going to kind of circle around